This is Lecture 6C for Calculus 2. It's an introduction to computing the volumes of solids. In computing the volumes of solids, these are complicated solids, not just ones that you memorize the formula for. But in trying to compute their volume, we do the same thing we always do in calculus. We don't know how to do it, so we approximate the object by little smaller objects whose volumes are well known, and the two that we use are the slabs and shells. There are several variations on the slabs and the shells, and the volume of a slab is the area of the cross-section times the thickness or height of a slab. The volume of a shell is the circumference times the height of the shell times the thickness of the shell. Okay, so once we've approximated it by these little objects, then we refine the approximation by using more and more slabs or more shells, a finer approximation across the object, and then take the limit and we call it what we get in the end, the volume. We do have to use algebra and some of the fundamental theorem of calculus to write the functions nicely so that we have nice definite integrals when we're done. But that's basically what you do to calculate the volume of shells, volume of solids. In this lecture, I'm going to go through the methods, try to explain the methods to you, and then there's another talk where some examples will be worked out. Okay, so first method I'm going to look at here is the slab method. Here's the idea. It's like the object you want to compute the volume of. Think of it as a loaf, an irregular loaf of bread, and you flop it down on the x-axis. So it's sitting here. Let me get a pen. It sits here on the x-axis between x equals a and x equals b. Okay, so there's your loaf of bread flopped down on the x-axis. You plop it down there, and then you slice it up. All right. And then you assume as you slice it up that every slice has the same height to it and the same cross-sectional area. So this is the area of this slice of bread, and we're going to assume that we made a uniform partition here, so this delta x is the thickness of it. So the volume of each little slice equals the area of the slice times the thickness, delta x. And that holds for all of them. Obviously, the area of this one is bigger than the area of that one, so the area varies across the object. We've made an equal partition, so we have delta x everywhere the same, although that's not necessarily, you could do something fancier than that, but we don't have to. Right. So basically, slab method, think of a loaf of bread, put it on the x-axis, and it's going to lie on the x-axis between x equal a and x equal b. Then you slice it up. And here's the method worked out. The volume of the slab will be its cross-sectional area, so that's the area, times the thickness, which is delta x, each little one. So here's the x-axis, partitioned into n subintervals. Right? The slab in each interval is assumed to have a uniform cross-sectional area, so A doesn't change within the slab. The volume in the slab, or the volume of each slice, is this, so the approximate volume of the entire well, you can say slab. Okay, leave it as slab then. So the area of the entire loaf of bread is the sum of all the areas of the little slices or slabs, and that would be just the sum over the different areas times delta x. Now, if you let n go to infinity, you are taking the limit, so you have this really refined partition, and in the limit, this finite sum becomes a definite integral. Most of the problems in working out these volumes is finding these expressions. It's not the setup, but you're going to have to kind of remember the setup. So when you have a slab, the volume is the integral of all the areas. See, in the limit, delta x becomes dx. This becomes the sum becomes a definite integral. This is just a blown up version of the slab. You see how the slab is like a loaf of bread sitting between A and B on the x-axis, and how you've divided it up, cut it up into these slices, each one of delta x width. Now there's a special case of the slab method, and that and this occurs when the object has rotational symmetry. Either you can look at it as symmetric in terms of rotation about the x-axis, or you can also do these calculations about the y-axis. So if you have a solid of revolution the way to handle this is you don't plop it down on the x-axis. Instead, you skewer it on the x-axis. So here's the x-axis right here, and your object, let's say it's some kind of weird fancy vase. It's like that. There we go. Oh, that's just too good. Okay, so here it is, skewered on the x-axis. I'm going to try to draw that better, but I haven't made much. Okay, so then you slice it up. Let me get a red knife. So I've sliced it up as before, but if you look at each cross-sectional area, the cross-sectional areas, because it's a solid of revolution, are all going to be circles. Right? The radius of the circle is y, which is some function of x. It varies with x. See, the radius is small here, bigger here, smaller here, a little bit bigger here. So it is just the y value is the radius. What is the area? We're using the same thing again. Volume will be the integral from a to b of the area, which varies with x times dx. And what's the area of a circle? Pi r squared dx. That's all. Solid of revolution is a special case of the slab method. It's a special case in that the cross-sectional areas are all circles. And you know the areas, they're pi r squared, and that's what you use in place of a. That is your solid of revolution. Here's just a picture of a solid of revolution. In this case, it's a sphere. This example is worked out in the lecture on examples for computing volumes. Okay. You see here, instead of plopping it down the x-axis, we skewer it. We stab it through with the x-axis. There it is. All right. And then each cross-sectional area, this is sliced up and kind of made so you can see that each cross-sectional area is a circle. And it has a radius. What's the radius of the circle? It's the value of y. Sometimes working out the area, the expression for the area is a little complicated, but you can kind of see the example. It's a slab with cross-sectional areas that are all circles. And here is the second variation on the slab method. It's actually a variation on solids of revolution. In this case, you have a solid of revolution. You see the outer edge of this whole figure. Disregard that inner dark green part for right now. You see that all those cross-sectional areas are circles of some radius. I'll call that big R, and the big R varies with x. Okay, then what's happened to this is a core has been hollowed out on the inside that also has circular symmetry. Right, and we'll call the radius of the hollowed out core r, little r, and it's going to vary with x. Or you could call this r outer, and you could call this r inner. All right, so now you want to know the volume of this. The way to find the volume is similar to finding areas between curves. You take the area of the entire outside as though there were no core hollowed out in it. So that would be the integral of r out pi r outer squared dx. And then you subtract from it the cored out area, which is pi r inner squared dx. And that's the volume. That's called a washer method because it's like a washer. You can see how it's a washer. So what you have are two radii. One is the outer radius, and the other is the inner. Okay. Here's what I was saying before. The volume of this washer is the volume of the outer surface as though it were solid minus the cored out part. And it's pi times big R squared, or I used R out in the other one, squared, minus pi times the inner radius squared. And both of these can vary with x. You can combine these into one expression, of course, and it looks a little bit like the area between curves. Right, that's the case of the washer method. That's the washer method. So you have slab, where it's the integral. I'm going to write this out for you. So for slab, you can see this in a group. It's not so hard to remember. The volume is the integral over the area. For a solid of revolution, then the volume is same thing, the integral over the area, but in this case the area is pi r squared, because if it's a solid of revolution, all of the circles are, all the cross-sectional areas are circles. And now for the washer, it's the difference of two solids of revolution. So it's the integral of pi, and I'll say, whoops, the outer radius squared minus pi times the inner radius squared dx. Okay. Now we have a different method called the method of shells. Here's a method of shells. In this case, you have some symmetry, and you plot this down. In this case, I skewered on the y-axis. You could do it on the x-axis too, but let's just do it on the y-axis. All right. And now, instead of cutting it into slices, you see, you could use the washer method on this easily. But instead of doing that, here's what you do, and it's hard to visualize. Once you see it, you've got it. Right? You can look at it as though you cut it into these different, like, if say there was more of this figure in here, you would have more of these shells. It's not showing you the whole thing. Okay. And each shell, it's as though it's an empty shell going around the y-axis. And what's the volume of the shell? Well, think of it this way. Think that you made that cut here. Right here, I cut the thing here and pretend it's made out of rubber or something, and then I straighten it out. So it's as though I have a circle. I'm going to look at the top of it. I cut it here, and if I straighten it out, what does it turn into? The circle turns into a line. It's as though I unwrap the circle. Now think of the cylinder again, the shell, and we're going to unwrap that shell. And what's it going to turn into? It's going to turn into, I can't even draw it right. Right, so when I unwrap the shell, it turns into a rectangular solid. Whoa, I'm getting better drawing. Okay, go back to the circle. If I unwrap the circle, how long is this piece of string? It's 2 pi times the radius of the circle, because it's the circumference of the circle all wrapped out. This point is this point. This point is down here. Now I'm doing the same thing with the shell. The point on this side of the cut is here. The point on the other side of the cut is over here. What is the length of this unwrapped shell? It's 2 pi times the distance out to here, which is x. The thickness of it is delta x, right? And the height of it is y, which is some function of x. So once you can see what you've done, you've taken the cylinder and you've flattened it out. These pictures are drawn much nicer in the textbooks. But you take and you flatten that cylinder out. Now it turns into a rectangular solid. What's the volume of it? It would be height times width times depth. So it's going to be f of x to get the height. The width of it is delta x. And the depth of it, which I'll call here, is 2 pi x. This 2 pi x is like the circumference of the shell. So this is the shell method. Go look at some pictures in the book if you don't see it from these scribbly graphs and drawings. So here's what I'm trying to draw, but stated in words. So you have an interval from 0 to b, that's in the x-axis, the shell. The shell is plopped down here, and it goes from minus b to plus b, so we're only going to look from 0 to b. Then you divide it up into little delta x's, so it's a whole bunch of nested shells. Let me get the pen here. So here it's divided up. Each subinterval defines a cylindrical shell of width delta x, and the height is y, and y varies with x. Okay. The circumference of each shell is 2 pi r, is 2 pi x. So the volume of the shell is circumference times height times thickness, and here you go right here, 2 pi x, circumference, height, y, thickness, delta x. And then you add up all the little shells and you integrate over them. And that's your shell method. It's a little, looks a little more complicated than the others. Here's another picture of the shell method. Here's the object. It has rotational symmetry. I've plopped it down on the x-axis, but I've skewered it with the y-axis. It's going from minus b to plus b. We're only concerned with 0 to b, although I'll give you an example where it's displaced, but just look at this for now. You cut it up. This was really a smooth curve, and the outline of it was y equals f of x, some nice function of x, not necessarily these stair steps, but as you cut them up into shells, you get all these cylindrical shells. Each shell has a width of delta x. The height is y, which varies with x. And the length all the way around is 2 pi x. That's the length all the way around, or the circumference of the shell. Those are your three methods. Slab method, with the variations of the solid of revolution and the washer. Then the other is this shell method.